we are now entering the chapter of nuclear physics, and for now we are entering the first topic, which we talk about the formation of a nucleus. How do we form a nucleus, or how do we break up a nucleus, and the energy associated to these kind of processes, the formation and the breaking up of a nucleus. So to study the kind of interaction that we have in the nucleus, right, we should probably start with some basic understanding of how electrostatic forces work. So I'm going to show you two scenarios over here, and I'm going to ask you what kind of forces are involved and whether they attract or they repel. Okay, so scenario 1 involves two charges. They are oppositely charged, one positive, one negative. So from understanding of electrostatic forces or Coulomb forces, you should know that opposite charges, they should attract each other. So in that case, they will try to move towards each other if they are able to freely move. So in this case, they attract. For scenario 2, if you have a pair of like charges, they should repel. In this case, positive, they have the same polarity, so they should have repulsion, so the force should point away from each other and they should try to move away from each other. So in this case, we can say that like charges, they will repel. So understanding this basic interaction between charges of different polarity or same polarity, we can try to discuss what will happen for this situation. So let's say we have eight positive charges being positioned in a circular shape. Okay, so all these charges are like charges, so we should expect that they should repel each other because like charges repel. So in that case, we should expect that they will all try to move away from each other because that's what repulsion means. So if we try to draw the forces experienced by each of these positive charges here, the forces should point away from each other. So we can expect that these are the repulsion forces experienced by this positive charge, and they will all try to move away from each other. So we say that repulsion will occur if they are all positive charges. Okay, so we're going to apply the same logic here to study an electron. Study a nucleus, sorry. So when we study nucleus, I'm going to bring back this example that we discussed here to try to understand why are we able to form a nucleus. Okay, so all nuclei, or plural of nucleus, are made of protons and neutrons. Okay, so if you talk about a basic hydrogen atom, there's only one proton, but as you move on to talk about helium, lithium, so on and so on, the number of protons and the number of neutrons will slowly increase. But no matter what, if you look into a single nucleus, there's only protons and neutrons. Okay, you have electrons, but electron is circling outside, orbiting outside the nucleus. So if we are focusing on the nucleus as the title of this field called nuclear physics, we're focusing on the nucleus, which is the inside of it. Okay, there's only protons and neutrons inside. Okay, so here I'm going to show you a cartoon representation of a atom, but our focus here is what's in the middle over here. We are focusing on the nucleus that is in the middle of this atom over here. So if we look inside of it, we can see that the constituents that make up this nucleus over here can only be either protons or neutrons. Sometimes there will be more protons, sometimes there will be more neutrons, I think somewhere around there. Okay, so but no matter what, it's only protons and neutrons. So if we are talking about protons are positively charged. Okay, they have positive charge. I think that's quite straightforward. If they're neutrons, then they are charge neutral. Charge neutral means by they are not positive, they are not negative. You can say charge zero or charge neutral. Okay, so my question to you is, why won't all nuclei explode? Because if you talk about a nucleus, there's only either protons and neutrons. You know that the neutrons will not interact in the electrostatic manner with the protons, because neutrons are charge neutral, so they are not involved in the repulsion or the attraction that we have been studying. So that left us with the protons. So we know that the protons are all positively charged. There's no negatively charged protons over here. So if all of these protons here are positively charged, shouldn't they all repel each other? So if they all repel each other, they should all try to move away from each other. So why are we still able to stick them together into this small space over here, forming a nucleus, even though we know that naturally they should be repelling each other, they should naturally move away from each other? So that's the question I want to propose to you all to think about. So So you should expect that all of these nucleus here should actually, if you study Coulomb force, technically they should all explode. So if they should all explode, there will be no formation of nucleus. If there's no formation of nucleus, there's no formation of atom. If there is no formation of atom, there's no formation of any kind of material, then there will not be anything existing in our universe. There will be no earth, no table, no nothing. Everything cannot be formed because you cannot form even a single atom. Okay, so something is missing in our big picture of study over here. Maybe our knowledge is a bit limited. Maybe there's something more to just all this electrostatic repulsion or attraction that we've been studying about. There's something more to it. Okay, so here's a question you can ponder on. Okay, so now, why is the nucleus not exploding due to the electrostatic repulsion of the proton? So here I'm going to discuss with you the interaction involved that allows the formation of nucleus even though there is an electrostatic repulsion. So here we have two positively charged representing two protons over here, and they are being placed, if you're talking about nucleus, they are being placed at a very small distance apart from each other. A nucleus has the size around 10 times 10 to the power of negative 15 meter. Okay, if you talk about nucleus, if you measure its size, right, it's around 10 to the power of negative 15 meter. So you call this as 1 Fermi. Okay, but don't worry too much about the names. So they are very short distance from each other. So if they are very near to each other, we should actually expect quite a strong, a very significant Coulomb force acting on each other, because we know that K, Q1, Q2 over R square, right? So if you reduce the R square, technically you will cause the force to increase. So since they're very short distance from each other, you should expect quite a significant Coulomb force trying to repel them away from each other. Okay, so that itself cannot explain why we are able to form a nucleus. To be able to form a nucleus, we need something to glue them together. So we need a stronger attraction, a much stronger attraction that can overcome the repulsion due to this Coulomb force over here. So now we are going to fill in the missing puzzle over here by saying that there must be another force other than the Coulomb force in play here. So there's something more to the electromagnetic force that I've been studying in the earlier semester. There's another force that is in play over here. And that another force here, we are going to name it as strong force. Okay, not we. The whole scientific community name it as the strong force, or sometimes you read it as the strong nuclear force. Okay, this strong here is not really an adjective. It is an adjective in the sense that the force is really strong, only they are able to overcome the repulsion. But this strong force here, you should actually think of it as a noun. Means that this force here has a name. The name of the force is called a strong force. At the same time, we can describe the force as being a very strong force. So this strong here acts as a noun. It is a name of the force. Just like Coulomb force is a name of the force, strong force is also a name of the force. But as the name itself depicts, you can understand that this force here, you should expect it to be very strong. Really strong, so that they are able to overcome this Coulomb force over here. So that another force must be stronger to overcome the electrostatic repulsion to bring all the nucleons together. So all the nucleons here means by protons and neutrons. So this strong force here will be the force responsible for bringing in all these protons and neutrons in order to form our nucleus over here. So we, as the diagram here shows, the strong force should be much stronger than the Coulomb force over here. So now we are only able to bring all those protons to be nearer to each other. So this strong force here is present between all nucleons, protons and neutrons. So previously when we studied about electrostatic force or Coulomb force, we see that if they are opposite charges, they attract. If they are like charges, they repel. So no matter what, in order for you to have electrostatic force, you need to have an electric charge, either positive charge or negative charge. But this is not the case for strong force. If you're talking about strong force, right, no matter you're talking about protons or talking about neutrons, whether it's positively charged, negatively charged, or neutral charge, those things are irrelevant for the discussion of strong force. Strong force will be activated. This strong force will exist between all types of nucleons, no matter if it is protons or neutrons. It doesn't look at what is your charge. Oh, if you're neutral charge, you cannot have strong force. No, it doesn't look at what kind of charge you have. No matter you are positive charge, negatively charge, or you are neutral, strong force will still exist. Okay, but for it to exist, you have to fulfill one very important requirement. Okay, so it's independent of their charge. The charge is irrelevant over here, but the requirement you need to achieve is as long as they are very, very close to each other. So you want these protons, you want these neutrons to be very, very near to each other, around the order of 10 times 10 to the power negative 5 meter. Okay, so if they are further away from 10 to the power negative 50 meter, then this strong force will not be significant. You will not be able to observe a significant strong force to attract them together. Strong force will only be activated, or strong force will only be significant when they are able to put these charges, these positive and these protons and neutrons, very, very near to each other, somewhere around the order of 10 to the power negative 50 meter. Then strong force will be activated, and since it's much stronger than Coulomb force, you are able to bring those protons and neutrons together to form your nucleus. So now to fill in the puzzle over here, why we are able to form a nucleus is because of the existence of a strong force. This existence of strong force here is much stronger than the Coulomb force. Thus, they are able to overcome the electrostatic repulsion to bring the protons and also the neutrons together at a small space, irrespective of the charge that protons and neutrons have. So in the next video, we are going to move on from talking about the interaction involved to the energy involved when we are forming a nucleus or we are breaking a nucleus.